All right, welcome back. So our next speaker is Amy Zhang, who's a professor at UT Austin. Also was an undergrad at MIT, so again, an excellent sign there. Her research focuses on improving sample efficiency and generalization of reinforcement learning algorithms. So we're sort of following up our reinforcement learning morning with a bit more with RL and generative AI. So thank you.
All reinforcement learning all the time. No, I'm very happy to be going after Dylan because I think he did a good job of setting up why we should care about reinforcement learning and looking at how RL can be used with LLMs. And so I think my talk is along similar lines, but it's going to be a lot more low level in terms of the details of what we really still need to do from the RL side and develop in terms of RL algorithms so that they're more useful for generative models and training LLMs. But also the other way around, right? Like there's a lot of nice ideas in generative modeling and supervised learning that we can carry over into reinforcement learning. And so first, I'm just going to provide a gentle introduction to reinforcement learning because I know this is a very cross-disciplinary audience, and so I'm hoping that you know giving the basics will be helpful in terms of understanding the later parts of this talk. Generative modeling, you know, a lot of the core ideas behind this are about likelihoods, about occupancies, about probabilities, probability distributions, whereas like reinforcement learning is really about this scalar reward and the idea that we want to maximize that scalar reward. And so how do we actually bring these concepts closer together is something that I want to talk about. And one way that we can do that is to just try to get rid of the idea of reward entirely, in which case, you know, like what are we doing reinforcement learning on, right? Like where is our learning signal coming from? And so I'm going to talk a little bit about goal-conditioned RL, and then how we can generalize this into something that we're calling self-supervised RL, which allows for zero-shot inference or extraction of an optimal policy at test time. And then we'll provide an example application of this zero-shot RL. Okay, so what is reinforcement learning? How does RL work, right? So typically we're assuming that we have access to some environment. We are the policy, the agent or model that we're learning is this policy that's going to take in the state from the environment and output some action. And we're also going to get back from the environment this scalar reward that I mentioned. And so the job of our policy is to try to maximize that reward over time, right? So it's a sequential decision-making problem where we're continuously taking in new states from the environment, responding to those states, taking actions that we think are going to maximize the future reward that we will obtain from the environment. And so as we do this, we're collecting this trajectory, right? So we start out in S0, we're going to take action A0 that brings us into S1, from which we will take action A1 and so on and so forth. And so the RL objective, so as written here, is that we're trying to maximize the sum over future rewards. We're going to add this discount factor here, so, and typically, you know, we'll use a value like 0.9 or 0.99, and that basically controls how forward-looking the agent is, right? It basically tells us how much do I care about present reward as opposed to future reward, right? And so all else being equal, we're actually going to prefer to get rewards sooner rather than later. If we are only going to get one chocolate bar in our lives, we'd like to have that today rather than 10 years in the future. Okay. And so then we now also have this expectation. And so then what I really want to show with this expectation is that this trajectory is being sampled from our policy. Right? This is not some stationary distribution. It's not IID collected from some data set. This is an expectation over trajectories sampled from our policy, collected from the environment, and not from a human. And so I'm just going to walk through how this one trajectory is sampled because we're going to look at this in terms of the probabilities, right? So our environment has one aspect of our environment is that there is some initial state distribution. With some probability, we're going to see some first state, S0. Our policy can also be represented as a distribution, so it's conditioned on the state that it just saw, and it's going to output a distribution over the actions that you can possibly take in this environment. The dynamics of the environment can also be represented as a distribution over next states, and then so on and so forth. And so we just keep doing this over and over in order to collect our trajectory. And so to just really highlight the differences between reinforcement learning and supervised learning and the similarities, if we're both supervised learning and RL, we're taking in these input observations, we're outputting something. In supervised learning, it's labels. In reinforcement learning, it's actions. In supervised learning, our objective is just to mimic the labels that we have in our data set, so we're assuming access to this labeled data set, whereas in reinforcement learning, we just have an environment. So we're collecting data as we go based on our policy, and our objective is to maximize the sum of rewards. And so if we think about this problem of Tetris, in the supervised learning setting, I'm requiring that I have access to some expert player who knows how to play Tetris, and for every state I see in Tetris, I'm just going to copy what that human expert is doing. So I'm only ever going to perform as well as that human player, right? Whereas in the reinforcement learning setting, I'm actually going to be using maybe the Tetris score as a learning signal, and so there's actually a possibility that I can outperform that human expert. Okay, so RL from a generative modeling perspective. The key idea here is that an agent iteratively interacting with the environment is a generative process. The process of producing that trajectory is generation. And so conditioning the policy can give us different outputs or trajectories. But the problem here is, again, generative models are trained on data. They're maximizing likelihoods. And so where do rewards come in? And so here I really want to highlight why reward is something that is really hindering RL. So here's just an example of the definition for a reward function in a simulated robotics, for a simulated robotics task. So this is from MetaWorld. And so you can see that this is very complicated, right? And so I think even just thinking about, how would I define a reward function to convey to a robot that I want it to get me a cup of coffee, right, is very complex. And so reward design is prohibitively difficult. Oftentimes, it requires expert domain knowledge because we don't necessarily just want to rely on a sparse reward signal, right? And so that means if we want to provide some kind of dense reward signal, it requires knowing what should that optimal policy actually look like, which is not a setting that we want to be in reinforcement learning. And then, based on sort of like all of the kind of like new results that we have with foundation models with these generalist agents, we would also be able to we would like to be able to train reinforcement learning agents that can also perform many tasks, right? And so now for every task, we also have to design a new reward function. This is going to be prohibitive. And so one setting in which we can kind of avoid all of this reward design is goal-conditioned reinforcement learning. So goal reaching has many practical real-world applications. So one example is just robot navigation or path planning and route optimization, chemical synthesis, autonomous driving, and various forms of games where there's some kind of goal state that we want to reach. And so what's the goal? So if we want to kind of go back to describing the goal-conditioned reinforcement learning problem from reward, the agent is now trying to reach any number of possible tasks within the same environment, right? So as long as I can define a goal in this environment, that becomes a new task. The goal is sampled at the beginning of the episode, and the kind of automatic definition that we can provide for this reward is that I'm going to see a reward of 1 if I've found my goal and 0 otherwise. So again, we want to move away from rewards, so how can we actually think about this in terms of probabilities? So instead, we can just look at the probability that the next state is our goal. And so then we can write our objective as follows, right? So now we're trying to maximize the likelihood that the next state that we're going to be in is the goal. So again, we can write this in terms of reward, and our reward is now just, again, this probability. So now we've defined reward in terms of probabilities over states, right? So this is much better than hand designing reward functions. And so this is a term that we're going to see a lot in the next few slides, and so I just want to formalize this a bit. And so the thing that we actually care about is this discounted state occupancy measure. And so one way of thinking about what this is if I have this ant, this agent, right, on the top, and so this is my initial state, what the discounted state occupancy measure is giving me is kind of just this average, this discounted average over all of the future states that this agent can end up in over the course of this trajectory. And so that's why you can see it as this kind of faded away, like blurring over this trajectory of this agent. And so I can, have multiple examples of this for different kinds of problem settings. And I can also define this term not just for this probability over future states, but I can also condition this on various things that I care about, right? So I can think about the state occupancy conditioned on whatever state I am in currently, or conditioned on the state and the next action that I take, and so on and so forth. Okay, so the dual of RL is actually something that has been studied for a long time, so these ideas are not new. So in the standard primal reinforcement learning setting, right, we're trying to solve this objective, which now should be pretty familiar to all of you, where we're trying to maximize this discounted reward. But in the dual formulation, we're actually going to switch out this optimization variable. And so instead of trying to optimize a policy that maximizes reward, we're instead going to optimize for this occupancy measure. And so, this idea of using occupancies, of thinking about RL from the probability, from the notion of using probabilities is not a new one, because this has already been explored in dual RL. All right. So we know that goal condition reinforcement learning is a setting where we can avoid reward functions. We know that we can actually design this reward to instead be defined in terms of probabilities. Now let's think about just completely avoiding that standard RL objective and instead define distribution matching as a way of doing RL. So we want to train a goal condition policy by minimizing this objective, right? And so here we're just saying that we want to minimize the F divergence between the probability distribution over states conditioned by our policy, and so that's why we have this theta parameter, because that's how our policy is parameterized. And then we also have some goal distribution, so this is our target distribution. We're saying that we want to minimize the F divergence between these two things. And so PG of S in the goal condition setting is a very simple target distribution. It just corresponds to a Dirac over our goal state. And so again, the intuition behind this is that we just want an agent to be at the goal state with high probability. So we want it to be able to find the goal, reach it, and stay there for as long as possible, right? That's how we're going to minimize this objective. And just to give a bit of a refresher on F divergences, there's different kinds of F divergences which are just give different measures over the distances between two probability distributions. And so this is a really intuitive way to understand what these different F divergences give us, right? So in orange, we have our target distribution. And in blue, we have you can think of this as the probability distribution over states of our current policy. So as our policy is learning and changing over time, we're getting closer and closer to that target distribution, and all of these different divergence definitions, you can see that they're all providing smaller and smaller values as those distributions get closer together. So the first question that we may want to ask is, does this F divergence minimizing objective, does this produce the optimal policy? And what does that mean? What we're really asking here is, if I take the original reward-based formulation of this goal condition RL problem, am I going to get the same optimal policy for minimizing or maximizing both of these different objectives? And it turns out that the answer is yes. We have this result that shows that these two objectives are equivalent. So how do we actually optimize this objective? We can just use gradients, right? So if we compute the derivative of that F divergence, it turns out that we get something that looks a lot like policy gradient, right? We have this first term, which is just the log probabilities of our policy, and the second term looks a little bit different, because with standard policy gradient, that second term should just be our reward signal. And instead, we have this density ratio. And so we have to be very careful to not call this reward. These are actually just dense weights. And the reason for that is reward, by definition, is stationary. It does not depend on the behavior of our current policy, whereas this term does. And so that's just this is just like, I guess I want to kind of spend a little bit more time on this to basically show you that this provides dense learning signal, right? Whereas if we were to replace that with the indicator function, which is how we define reward in the goal condition setting to begin with, this would be much harder to optimize. So what does this learning signal actually mean? So we have this really simple problem where we just want the policy to find this goal location, which is just on this right-hand side, like middle, where the red dot is, right? So the red corresponds to high value. And so we can see that across these different F divergences that we can use, at first, when the agent hasn't yet encountered the goal, we can see that the occupancy of this policy is actually spread uniformly over this entire space. As soon as we see the goal for the first time, then all of the weight starts to concentrate on that goal location, and you can see that even though the behavior for these different F divergences is slightly different, they're all basically doing the same thing and trying to concentrate all of their probability mass on the goal location. So there's also connections between this and exploration. So a really simple form of exploration that's used in reinforcement learning is to just maximize the entropy. So what are we maximizing the entropy of? We're trying to maximize the entropy of the policy, of the next action distribution from every state. And so you can see pretty clearly from this definition that in order to, the policy that maximizes entropy is going to be one that just outputs a uniform distribution over actions. So it turns out that our objective is doing something somewhat similar, but instead of maximizing the entropy of the policy, we're actually maximizing the entropy of the occupancy of our policy. And so, again, we can kind of look at how the behavior differs in this very simple grid world example. So the first two are our method, and the last one is using that standard policy entropy maximization. And it should be pretty obvious to you that if we're just trying to maximize the entropy of the policy of just outputting a uniform distribution over the actions, it's not actually the most efficient way of performing exploration and encountering new states. And so we do actually see that on the right-hand side, it takes a little bit longer to spread out across through the state space, encounter the goal, the red dot, and then concentrate all our probability mass there compared to the first two. Okay, so there's all these nice, these are some nice demonstrations of what you can do for goal condition problems, but a lot of problems that we care about are not goal reaching, right? So if I want a robot to just clean up my living room, or if I'm trying to book a flight, I can't easily describe those tasks as a goal, right? Like I can provide a picture of my living room clean to a robot, but there's many possible ways in which my living room can be cleaned. I don't necessarily care which one the robot uses. And for finding a flight, there's a lot of things that I might care about, right? Like I might care about what time of day I fly, I might care about my airline, I might care about how many layovers I have. I don't necessarily just care about shortest path to my destination. And so we'd like to generalize these ideas from the standard goal condition setting to general tasks, something that can be described by any possible reward function. And so before I do that, we're again just going to look at that occupancy measure that we saw before. But now we're calling it a successor measure. So it turns out that given a task reward function R, I can rewrite the standard RL objective, this Q function that I'm learning, which I haven't really done a good job of defining. But this Q function, I can write it as this sum of this product of my state action visitation distribution and my reward signal, right? And so I'm just writing it down in various forms. And so my Q function can be written with respect to this successor measure. And so this successor measure is just a generalization of the occupancy measure that we saw before, right? So this is now providing for us the probability that I'm going to end up in state ST and action S plus and A plus if I started in state action SA. And so if we look at this update, right, for learning this Q function or learning this state action visitation distribution, this Bellman equation is affine. And that just means that I can write this down as a set of linear equations. I can describe it, all possible Q functions, as a basis set phi and some bias term. And so that means that I can think of this convex hull of valid solutions. So these are all of the possible Q functions, all of the possible policies that obey the dynamics of my environment, subject to the constraint that phi w plus b has to be greater than or equal to 0, right? Because we're talking about probabilities here. So every point in this convex hull corresponds to some w term, this weight term, which I can map to a policy. And so for each of these policies, there is some reward function, infinite reward functions, for which that policy is the optimal policy. And so now we just need to learn this mapping between reward functions and policies in this convex hull. So I'm going to, again, take this successor measure, which is just this generalization over state action visitation distributions. They can follow the exact same Bellman equation as state visitation distributions. So all I've done here is just plugged in this linear formulation. And for any reward function, I can just simply solve this linear program for W. And so in practice, that's what we can do. And our loss objective is using the exact same standard, reinforcement learning algorithms that we typically use. So this equation is just the temporal difference error, but I've just plugged in this phi w plus b in place of q here. And we just need to minimize this for all possible policies. And this gives us a representation that is not dependent on any policy and is truly a universal representation. And so the benefit of a method like this is that we can now perform simple inference on any reward function, and it allows for zero-shot extraction of a near optimal policy, right? Because all of this is approximate. It allows for a fast adaptation setting where we can use this to extend the previous method FPG by providing better representations for state visitation distributions. And we can extend this to offline settings. But basically, this is a method that is ideal for environments where we don't have access to reward, right? So this is a self-supervised method. And here self-supervision just means, right, we don't have access to reward. We only have access to environment or some offline data set of transitions. And because we're doing this self-supervised pre-training by just kind of like sampling different reward functions from that convex hull and learning how they map to optimal policies, it means at test time, as soon as we get any kind of reward signal or any kind of information about what our task is, we can just find what W it corresponds to, get our Q function, get our optimal policy out, and so it's zero shot in the sense that we don't actually have to train our policy anymore at test time. And so you can think of what we're learning during this pre-training phase as a behavioral foundation model. Right? It captures all of the policies and all of the tasks that we could possibly care about downstream. And we're just front-loading all of this computation from when we've received the reward signal to before we have received the reward signal. So here's just one example of an application for zero-shot RL. And so we just called this RL0. And so the first step, or I should maybe provide a little bit of context for what we're trying to do here. So we're assuming that we're using PSM, our proto-successor measure method, in an environment. And so we're extracting all of these policies that we can care about. But we would now like to be able to convey our task in terms of language, right? And so this policy has never seen language before, or behavioral foundation model has never seen language before. So one thing that we can do is try to hook this up with a VLM, a pre-trained VLM. And so in the first imagine step, we're going to use a fine-tuned VLM to generate video trajectories. So now we're mapping from language to video. We're going to project, right? So these generated videos are going to be generated in whatever video domain that the VLM was originally trained on. And so it's very likely that this is going to be very different from whatever target domain that we actually care about, that we've actually trained our behavioral foundation model on. So in this project step, We're going to map from our generated observations to real observations in our target domain. There's a lot of different ways in which you can do this, and so this is really just sort of like a general framework of how this could work. So one example is if you have a pretty good assumption that your target domain that you care about is similar enough to this video domain that the VLM was trained on, you could just do nearest neighbors in order to do this projection step. So now that I have a trajectory or a set, right, of states that I want to be in, then I can just assign reward to any of those states, and I can now do this kind of zero-shot policy extraction with PSM and extract out this optimal policy that will exactly imitate that video trajectory or match that demonstration. So this is just sort of one example of what we can do with this kind of self-supervised RL method. And these are supposed to be videos, and so, anyway, just imagine that they're actually performing actions. Obviously, in the first one, she's trying to do a flip, and the last two, they're doing different kinds of yoga. But again, this is an example of what our target domain looks like, and so we have this very simple walker, but it's a similar enough kind of like humanoid figure. And so you can see that it actually kind of has figured out like a pretty good projection from the target like video demonstration into our target domain. And so we can actually extract out these policies. Oh, and the main thing I want to note here is that you don't have to even use a VLM. So you could use a VLM if you want to just describe tasks in terms of language, but here we're just taking videos off of YouTube and saying, like, if I have some target video of the type of behavior that I want to exhibit, I can just use that directly and extract out the policy zero shot in my target domain. Okay, so just as a takeaway, I'm trying to show the ways in which we can use RL for training sequential generative models. We can also think of using these approaches for training LLMs from scratch. So rather than doing supervised learning or supervised fine-tuning, you can think about using these approaches to train on internet-scale data where we don't have access to reward functions, right? And so we need more research on RL methods looking into this dual perspective, into thinking about RL from occupancy measures rather than reward. I'd like to see more research on these kinds of self-supervised methods, again, because it's a way to take RL and apply it to the kind of foundation models that we've been seeing recently. And I really like this cartoon because I think that it's a really good example of what is happening when you do supervised learning, right? So a lot of real-world problems, they are truly RL problems. They are truly sequential decision-making, but often it's intractable to think of it that way, and so we act more myopically. We just think of it as just a bandit problem or just a supervised learning problem, and then we end up in situations like this where you're just like, okay, I got it wrong. Let me just stir things around and try again. Right? Whereas maybe if we actually think of these problems from an RL perspective, then we won't need to do this. And there's this really nice Nature paper by Yar and Gall in 2024 that basically is showing that the way that we're training LLMs these days is that they're generating so much data that goes back on the internet and gets recollected to retrain that generative model, that we're basically poisoning the data sources of the foundation models that we're training. And one thing that's happening is that as you sample from these generative models and they go into the data sources that we collect from, the tails of our data distributions are disappearing. And so that's one way in which we're kind of poisoning these models. So if we instead re-examine the ways in which we train generative models and think about them from an RL perspective, think about this retraining sequence as an RL problem, then it's a natural way of incorporating exploration, of making sure that our data, the data that we generate from our model stays diverse, because we're keeping in mind that we're basically outputting data for the next model that we train. And so, I think that RL is definitely having a bit of a moment, what with Sutton and Bardo receiving the Turing Award last year. But I still think that there's a lot that can be done in terms of future capabilities of RL. And so I think that RL is still a really interesting area to continue to do research in and to explore in. And so this is kind of a pitch, I think, to focus more on RL research. And with that, I'd like to thank my group for a lot of the research that I talked about here today, and I'm happy to take any questions.
All right, thank you. So do we have questions? There's one back there.
Hi. Thanks for the great talk. In the case where the goal is too far away from our initial state, what are your views on hierarchical planning and scale-based RL?
Oh, interesting. Yes. So actually, I thought that question was going to go in a different way. And I thought you were going to say, what do you do if you don't have any learning signal because your goal is too far away? And so then I was going to plug FPG, but that wasn't your question. I think that hierarchical methods are a fantastic way of solving those kinds of really long horizon problems. But hierarchical RL typically is assuming that you have additional knowledge or there's additional structure in the problem that you can leverage, right? So in hierarchical RL, the idea is that you have a bunch of low-level policies. You're basically dividing up the problem. So you have a bunch of low-level policies that are skills, and then you have a high-level policy that is now making decisions in this abstract action space over these skills. But the assumption that you're relying on is that these skills can be reused, right? There's enough structure in your problem that you can define skills that you can use over and over and over again. So, obviously, I think that I can design some kind of adversarial environment where, like, a hierarchical RL method is just not going to do better than flat methods. But you're right that I think for real-world problems that we care about, hierarchical approaches can make a lot of sense. Yeah.
Thank you.
Thanks.
Other questions?
Hi. Thanks for the nice talk. I had a question. So you started out kind of making this comparison between RL and kind of standard supervised learning, kind of cross entropy laws versus kind of the RL objective. And so in kind of more on the supervised side, there's a little bit of a convergence just with the power of the type of density estimation you can do, where you can kind of just formulate normal supervised learning as a type of posterior prediction task, and just if you don't apply like a Gaussian density and so on, it starts looking very, very similar to kind of generative models and so on with normalizing flows. And so like in a way, like this action generation, I mean, that's just a complicated generative model. Do you feel like these things are just converging into kind of one type of formulation, or do you still see some fundamental differences?
Yeah. Yes. So I have a longer version of this talk where I go into more details of sequential generative models, right? You can frame them as an MDP. You can think of a generative model as actually like both a policy and like a learned dynamics model. So in that sense, I think that there is some convergence like across these ideas. But I think my take on why that's interesting is that I think we should be using reinforcement learning to train these generative models. I don't know if that answers your question.
Yeah, no, I think that's what you see also with the post-training. I mean,
Yeah.
All right, thank you.
Yeah. But so with the post-training stuff is in particular really interesting, right? Because if you think of the like internet-based model, right? The language model that's trained on autoaggressively on the internet data, you actually shouldn't think of that as a policy. You can think of it as a policy, which is dangerous, but it's actually a dynamics model. It's really just learning what are the rules of grammar, like what are logical steps that I can take. But it's really the SFT fine-tuning that is learning a policy that we actually care about, right? And so then that SFT step, you can also think about instead learning that with RL, right? So which means instead of doing imitation learning, we could also take in a bunch of that suboptimal data from the internet and basically learn a policy that's more robust, because we're learning how to go from suboptimal data and steering our model towards the high quality data in the SFT data set. So that would be one example of a way, I think, of improving on the SFT step using RL.
Right. Thank you.
Hi, Amy. Thanks for a great talk. And in your RL0 work, I do have questions. Given your image trajectory is generated, will there be a problem of drifting if the horizon is too long?
Sorry, do you mind repeating that? So you're concerned about some type of drift in long horizon problems?
Yes, because that's your image trajectory is generated. I'm not sure if the generative models can guarantee the image in the trajectory can be generated very well in a long horizon.
So are you talking about like compounding error that can occur in long horizon problems with rolling out a policy?
Especially in your RL0 work. Yeah.
In the RL0 work in particular.
Yeah.
So there isn't really an issue of drift in long horizon problems, because we're getting a trajectory from the VLM, right? So that's supposed to encompass like what is the entire policy behavior over the entire horizon that I care about. And so we're really, to take kind of like the earlier work on F policy gradients, we're really trying to find a policy that maximizes all the probability, the occupancy of the policy in that trajectory, in all of the states within that trajectory. And so you don't really have a problem of drift, because you're not rolling something out anymore. You're really just, you've kind of like squashed the occupancy of the policy into saying, this is the set of states that I care about. Just spend all of my time in those states. And so this is also a reason why I think that for a lot of problems, this occupancy type of a perspective to RL makes a lot more sense than reward, right? Because especially if your reward model is something that's learned, it's something that's really easy to hack, because you're sampling again and again from this learned reward model. You're going to encounter errors, right? The fact that you're trying to maximize this signal from this reward model means you're even more likely to stumble upon and leverage these errors. Whereas if you have error in a target distribution, it just means you're going to spend like epsilon more time in some state. And so it doesn't have the compounding effect that you have with a reward signal.
Okay,
I hope that
makes
answers
sense.
your question.
Thank you.
Thank you.
Do we have more questions? Can I ask a question about computation?
Yeah.
I mean, how much does this cost to do all of this training in front before you do your zero shot?
Really hoping I was going to just like shove that under the rug.
It sounds like, it's kind of like magic, but there must be a cost up. The
Yes.
cost is up front, right?
Yes, exactly. And I kind of hinted at that earlier. But yes, there's no free lunch, right? We're really just front loading that computation. So instead of saying I have to wait to perform this computation after I find out what my task is, I can just do all of that up front. And I think with sort of like, again, the training frameworks that we're leaning towards today, right? Like what Dylan was also saying, right? With LLMs, like there's a huge amount of computation and data that's being fed into learning that base model, where you don't know yet what are the downstream tasks that you care about. And so this framework is kind of us saying, all right, this framework makes a lot of sense. Here's how we can bring RL into that paradigm as well. But yeah, no free lunch, unfortunately.
All right. Last chance for questions. All right, I don't see any, so let's thank Amy again.